Dun, 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 dun. Okay, we find ourselves back in space for this problem. This is 33.2 for the unit of rotation. Here, we're once again looking at angular momentum conservation. So a lot of I omegas equals I omegas here. In our problem, in order to kind of ignore the world of friction so that we can just have nice conservations, we have we have two astronauts in deep space, and they're connected by a 22-meter rope. So they're just kind of out there. These astronauts are rotating at an angular velocity of 0.48 radians per second around their center of mass. And the mass of each astronaut, including the spacesuit, is 97 kilograms. We're going to pretend the rope has negligible mass here so that we don't have to worry about its funky mass distribution. Okay? One astronaut, though, pulls on the rope, and they shorten it to 14 meters. What's the resulting angular velocity of the astronauts? So let's just draw like a tiny little picture here, nothing too fancy. We're going to have an astronaut over here, and an astronaut over here. And they're connected via some rope or via some tether. And that entire rope or tether has a length of 22 meters, which means from the middle to each of the astronaut, that's 11 meters. My astronaut on the right doesn't have eyes. Now they do. Now these astronauts are rotating at an initial angular velocity of 0.48 radians per second. Now when the astronauts start like pulling in on the tether so that they get closer together, so that there's only a distance of 14 between them, 7 on each side for each of the astronauts, we know that these astronauts should start spinning faster. If you've ever watched figure skaters, whenever they pull their arms in, they close up that moment of inertia, and because that value has changed, they've brought things closer into the axis of rotation, they're going to start rotating faster. Same thing happens for stars as they collapse. As you have a large star collapse into a white dwarf or even a neutron star, they can start rotating much more rapidly because that mass is closer to that axial rotation point, so that axis of rotation. And that axis of rotation is going to be the center of mass, which is exactly in the center of this rope. So this is what we have in the beginning. Afterwards, it's going to be the same picture idea. We've got two astronauts once again, but they're just going to be a lot closer. Okay, because we've shortened the tether. So on this tether, it's like 7 and 7. Now, the question from this becomes, if we want to use this conservation of angular momentum, I omega equals I omega for initials and finals respectively. What are the moments of inertia of an astronaut? Because if I look at my best friend, astronaut is not a thing on this chart. And that's kind of like a weird, like, well, are they cylinders? Are they long uniform rods? Like, what are these things? Because the rope is massless here. Well, if the rope is massless, then we really don't need to concern ourselves with the rope. These are just like two objects rotating about a center point. Yes, they're connected by a rope, but the rope doesn't have mass, so it doesn't concern us in this problem. It's just facilitating that rotation. Now, we know of other scenarios where masses rotate around objects, like planets rotating around our star, our sun. We can consider our humans and the planets in these type of situations as being point masses. Instead of saying we're some human shape out here, these humans are just dots. And if you recall earlier on in the year when we talked about F equals ma and drawing free body diagrams, we pretended that complex shapes were just dots, or the entire mass was at one location, the center of their mass. So now we just have dots going around in these circles. And we know that for dots, or a point mass, we know we have a moment of inertia of that. The moment of inertia of a point mass is just mr squared. So what we have initially is a moment of inertia, mr squared, for astronaut 1, added to the moment of inertia of astronaut 2, and then both of them each have their corresponding angular velocity. So we could write this as mr squared omega I for the first astronaut plus mr squared omega I for the second astronaut equals, and then for our final setup here, it's the same thing, but with new radii, right? So it's still mr squared, but for the final radius position, times omega f plus some mr squared for the final position of omega f. That's the full setup we have here. Now, luckily for us, some of these values can actually be simplified quite a bit here. What we might immediately notice is that every single term here has a mass associated with it. And both astronauts are the same mass, which means every single m term here is the exact same, which means they can all be divided out. All of the m's have gone away. If we wanted to, we could multiply by 97 kilograms each time, but we don't actually need to. Furthermore, by our diagram, we know that each astronaut is 11 meters away initially, and then 7 meters away at the end, which means that this r squared omega on this position here is the same as this r squared omega, which means that I could write this as 2 r squared omega I, where this is the initial radius. And that will be on the right side, if we follow that same principle, 2 rf squared omega f, which means that the 2's can go away as well. Whoop, whoop. Which means at this point, we just really have a ratio of distances you are away and what your angular velocity is. And this idea will actually come back later on when we start talking about planets going around for their perihelion and aphelion, which are words we've never talked about yet. But I digress. This means that this problem is pretty easily solved. We can just say it is 11 squared by their initial angular velocity of 0.48, and that's going to equal 7 squared times their final angular velocity. We could either divide by 7 squared, or if you know your multiplication tables, like a good student that you are, 7 squared is 49. So those are going to go away. And then we could divide by 49 here. Now it's just a matter for the calculator. 11 squared is 121 times 0.48 is 58.08. And then divide by 49 gives us a new angular velocity of 1.19 radians per second. So we do see here that our astronauts, as they've closed that distance, as they've pulled that tether in, as they've shrunk and become closer to their axis of rotation, their final angular velocity has increased just like we predicted, just like a figure skater who pulls their arms in. So this problem is finished. We've got one more to do, but until next time, adios, and take it easy.